So this is a diagram actually showing multiple forums, but really just to show how complex the AI data center these days become. Basically, you're actually looking at multiple segments of the networking actually needed enabling the AI compute to work. So this is actually have a scale up component, scale out component, and scale across component, just on the back end of AI networking. And you still have to take care of the front end. That's where all the data center service is interfaced to the end user request. So I won't dive in too much there, just set the background. So here just show you how intensive the fiber infrastructure needed for these AI data center. This is actually some of the pictures showing one of the AI data center. You can see the dock above all the compute. You actually have layers of pathways for fibers, cables to actually lay out and pass through from one part of the compute to the other part of the compute. Sometimes going from one side of the building to the other side of the building, even between buildings in campus. So the fiber number now, sheer fiber number inside the data center start to become huge, even though each segment could be just up to like 1-2 kilometers. But there are literally millions of these cables actually running between point A and point B. So you add it up, actually start to become million kilometers right there. So this has really become very large segment of fiber deployment. And to address these problems, certainly multi-core fiber is one of the elements or tools now hyperscalers start to consider. And like 2x2 is a really simple example, but that's a very prime option for using multi-core fiber to address the pain point for these hyperscalers. And example here is a 2x2, so you can actually have some key benefit just by deploying 2x2 versus just a single core fiber. You can cut down the number count immediately by 4, and you can actually reduce the number interface between fiber, and you can greatly reduce the weight of these fiber, and you can also provide much higher density in terms of layout of these fiber cables. So the benefit actually is surprising. Some of these customers tell us just the sheer weights of these fiber cable can be 100 pounds per foot. If you think about it, it will actually require very intensive foundational build out for each of these buildings. So as a result, not only cost, but also space, but also the time actually to get these AI data center built. So there are these area of cost or pain point. You don't realize what fiber actually can do, or you can help these hyperscalers to actually do a better job. And additional benefit I mentioned, I think Alan mentioned earlier by IEEE, because if you go to the next level of data speed from 200 gig per lane now to 400 gig per lane, you actually start to hit dispersion problems. And traditionally, we use CWDM, basically coarse WDM wavelengths to take care of this, use less fiber. But now, if you just use CWDM, you're going to start to see dispersion problems, actually, even just for 1 or 2 kilometers. So these are the area I think we really had to start to plan. And one more additional benefit is we all know right now the channel counts of these data center optics start to go up a lot. Right now we're really 8 lanes, and people already start to talk about 16 lanes, even 64 lanes. So the more you go, the fiber interface also start to become a bottleneck. So this additional benefit, you can actually reduce the footprint just on the fiber coupling side. You may not see it, but when we built transceivers, we had to worry about these things. So this is an additional benefit. Here's just to show why we had to build transceivers, actually look at the infrastructures, because you can actually build these boxes to do single mode to multi-core converters. Sometimes in industry people call it a FIFO box. But these come with the expense of additional costs, additional box, additional reinforcement, additional cost to actually build these boxes in the infrastructure. So again, all our AI data center customer, they are focusing on to produce the largest basically token per second or token per dollar token per watts for customers. So any space allocate to other things they can't allocate for compute. So this has become one of the bottlenecks. So we are basically here to develop a native so-called multi-core fiber native transceiver. So customer does not have to do conversion. They can directly plug multi-core fiber directly into transceiver. So you can actually have much cleaner deployment and much lower cost and space efficient. And at OFC this year, we actually demonstrated we can build now 800 gig transceivers with multi-core fiber. So this is actually built inside a transceiver with a multi-core fiber converter, really. So we can actually terminate it directly at the receptacles of the transceiver with a multi-core input and output. Actually, industry first 1.6T multi-core fiber transceivers now. These are just to show you a snapshot of how we build these transceivers and actually produce really, really good performance on the transmitter and receiver. So customer basically can deploy these transceiver without worry about additional link budget, additional pain they need to have to deploy these multi-core fiber. And this is a chart to show if you really want to scale the data center, you actually had to go a lot bigger now these days, not only just one building. You're talking about these multi-gigawatt level AI data centers. You actually had to have many buildings in a campus site, and sometimes you had to go a few kilometers, and at times you even need to string together a few buildings about 10 to 20 kilometers apart. So these are the area also start to see fiber issues, and you can actually, again, meaningfully address a dispersion problem by deploy MCF, because you can almost go 4 times longer distance with just a single wavelength like 1310 instead of using a CWDM. Typically now these days deploy in this kind of networks. And higher density, we are talking about for scale up. AI data center right now, like I said earlier, the scale up portion is where you have the highest bandwidth density actually coming out of the compute. If you're looking at like NVIDIA GB200, they call it NVL72, each one of these servers, basically each one of these NVIDIA GPUs, they actually have 7.2 terabit per second coming out of each of these server chips. So literally you have 10x more bandwidth. So what that means is if you are running at 200 gig per lane, you literally had to have 36 or 32 lanes coming out of these transceivers. So literally, if you're looking at how much lane coming out, you really start to worry about how much density you need. So we are talking about you can have a 4x improvement if you use multi-core fiber as a coupling element and then directly coupled to multi-core fiber. So this additional area, you can actually use multi-core fiber for this kind of applications. And then looking at the multi-core fiber deployment status, standardization is important. I think earlier commented ITU traditionally has been the standard body to write the spec for fiber. But unfortunately, I think multi-core fiber right now, I heard about starting a project, but not yet get started. So this is the kind of area I think the community need to come together and really start to work on it. And I think the ecosystem building is important. So this kind of need to get the whole end-to-end infrastructure in place. Fiber, transceivers, termination, splicing, connectors. So all these need to come together. And for deployment, because we do anticipate, because of AI growth in the next couple of years, they will start to have 1 or 2 hyperscalers really start thinking about deploy in the next 2-3 years. So if ITU are not acting fast enough, they maybe start to have activities like multi-source agreement. So at least we start to get a commonality of, this is called a networking elements, including fiber, to be somewhat standardized. So this is the activity we're anticipating coming up.